In this clarification video, we compare two matrices that can appear for the same undamped two-degree of freedom system. From the second order equation, we can write the acceleration equation as q double dot equals m inverse kq. To make the notation shorter, we call the matrix m inverse k by the symbol script d. For this two-degree of freedom example, D is a 2 by 2 matrix, so it has two eigenvalues. When we write the same system in state space form, the A matrix is 4 by 4, so A has 4 eigenvalues. The question is, how are the two eigenvalues of D related to the 4 eigenvalues of A? First, let's look at the eigenvalues of D. The eigenvalue equation is d phi equals mu phi, where phi is an eigenvector and mu is the corresponding eigenvalue. Since d is m inverse k, we can substitute that into the eigenvalue equation. Rearranging gives k phi equals minus mu m phi. But for an undamped mass spring system, the usual natural frequency problem is k phi equals omega squared m phi. Comparing these two equations shows that mu equals minus omega squared. Because D is a 2 by 2 matrix, it has two eigenvalues. Mu1 equals minus omega 1 squared and mu2 equals minus omega 2 squared. We use the symbol mu for the eigenvalues of D. Later, we use lambda for the eigenvalues of the state space matrix A. Now, we look at the eigenvalues of the state space matrix A. The eigenvalue equation is AV equals lambda V, where lambda is now the eigenvalue of A. Because the state vector has a displacement part and a velocity part, we split the eigenvector V in the same way. The upper part is phi, which represents the displacement shape, and the lower part is psi, which represents the velocity part of the eigenvector. When the block matrix A multiplies this eigenvector, the top block row gives psi, and the bottom block row gives d phi. Matching the two block rows gives two equations, psi equals lambda phi and d phi equals lambda psi. Now, we substitute the first equation into the second. Since psi equals lambda phi, the second equation becomes d phi equals lambda squared phi. Now, we compare the two results. For D, the eigenvalue equation was d phi equals mu phi. For the state space matrix A, we just found d phi equals lambda squared phi. So the connection is lambda squared equals mu. From the D calculation, the two eigenvalues of D are mu1 equals minus omega 1 squared and mu2 equals minus omega 2 squared. So mu1 gives lambda equals plus minus j omega 1, and mu2 gives lambda equals plus minus j omega 2. This is the doubling effect. Each eigenvalue of D produces two state space eigenvalues, because lambda squared equals mu gives a positive and negative square root pair. This is why the 2 by 2 matrix D has two eigenvalues, while the 4 by 4 state space matrix A has 4 eigenvalues. The state space form does not introduce new natural frequencies. It represents each frequency using two eigenvalues, plus j omega and minus j omega. These two eigenvalues form a complex conjugate pair.